there are a few more topics to cover in the synchronous machine section. So mainly, starting off here, so you went through how to draw the phasor diagram for the synchronous machine. So you have few terminology here. So if you look at the phasor diagram, you have the terminal voltage. That's the voltage at the terminal of the synchronous generator, and this is the E. That's the excitation voltage. That's like the back EMF. All right, thank you very much.
62 numbers that were
okay.
To staple some, because the first piece, the first piece came out, but I put in the same.
Okay, yeah, I'll keep it like that.
Yeah, 50 staple, two papers.
Okay. All right, thank you very much. Yes, yeah. Right. Thanks. So the angle between the terminal voltage and the excitation voltage is called torque angle. That's the parameter we write as delta. And then you have the armature current. So that armature current has a phase angle with respect to the terminal voltage. That's the, let's say if you consider it as a AC source, that corresponds to the power factor, how much it lags or leads the terminal voltage of the synchronous generator. So this phasor diagram is very important. You'll work with it if you are doing power system analysis in the next semester. You'll probably encounter this quite a lot, the phasor diagram of the synchronous generator. And then there are a couple of other topics that involve these synchronous generators. One is synchronization. So synchronization means that you are connecting the synchronous generator to the grid. So there are certain requirements that you have to fulfill when you connect the synchronous generator to the grid. So the grid is like a fixed source. It has sinusoidal varying voltages and then phase shifted. The synchronous generator, depending on the speed, the frequency at the terminal changes, and the magnitude changes with the excitation field winding currents. So there are three criteria. So for example, if you look at the AC waveform, so let's say this is the grid voltage, and then you have, let's say this is the grid voltage for one phase, let's say phase A, and then you have another phase, phase B, and another phase, phase C. So let's say this is phase A and B and C, for example. This is the grid voltages, and then so this is like three terminals. This is connected to the grid, and then you have your synchronous generator here, and you have three terminals here. So we need to connect these two at some point. So there's a synchronization mechanism where this, at some point, this breaker turns on. So let's say this is phase A, B, C, and then so you're running this synchronous machine at a certain speed. So let's say this is the synchronous speed, and then this terminal voltage has some different waveform, or let's say phase shifted slightly. So let's say this is the synchronous generator terminal voltage. Terminal, that's the voltage at this point, and this is the voltages at the grid side. So in order to turn this breaker on, that's called like connecting it to the grid, you need to synchronize the machine to the grid. So there are three requirements. So what requirements do you think you need to fulfill to connect the synchronous machine to the grid? When at the point we turn this on, the main criteria is it can't conduct a huge current and then trip or burn out. So it has to be some seamless transition between the two sources. Any ideas what criteria have to be fulfilled? Yes, yeah. So this this voltage magnitude, let's say if you consider individual phases, the magnitude of the phase voltages have to be close to each other. And then frequency has to be the same as well. So that means you need to measure the frequency here and then control the speed of the prime mover. So that's, let's say you have some kind of prime mover here. It can be a diesel engine or a turbine or something here that runs this. So you need to control that to achieve that frequency close to the grid frequency. And then the phase of the voltages have to be the same as well. So if it was out of phase, let's say for example, if you consider the grid voltage and the synchronous generator voltage, and if you turn it on at some point here, let's say for example, you have this amount of voltage difference between the circuit breaker. So it's like a short circuit. That amount of voltage is going to be short circuited. And then that's going to cause a huge current if the phases don't align as well. So this has to move exactly same phase as the grid phase voltage as well. In addition to that, there's a fourth criteria that's called phase sequence. So that's this ABC has to match with ABC here. So if you have A here and then C and B to the other phases, then that will trip as well. Then it's completely off. So those are the three criteria. This phase sequence has to be the same, the voltage magnitude has to be the same, the phase has to be the same, and the frequency has to be the same. So to synchronize those four criteria have to be met. So modern techniques have like electronic systems that measure the voltage here and do certain form of control. But the most primitive approach is you connect a lamp here. It can be like an incandescent lamp. And then three incandescent lamps between these two terminals. And then this lamp will like blink on and off at a certain frequency, which is the difference between the two frequencies. If the frequencies are the same, it either completely turns off or completely turns on or starts blinking at a very low frequency. So if you are coming close to synchronization, it tends to blink at a really low frequency, and you know it's coming close to synchronization, and then that's the point you turn on the breaker. So that's called the dark lamp method. So that method is used for old technology, but now modern technology has like microprocessor-based control systems to measure grid voltage and the terminal voltage and control itself. So that's one aspect that we had to cover, and then the other part is the power transfer. So once you've synchronized it, you have two parameters that you can control. So let's say you've synchronized the synchronous generator to the grid. So now it's connected to the synchronous grid. So let's say this is connected to the grid. So usually we draw the grid like a bus like this. So this is like a fixed voltage that doesn't change. So the grid is huge. The variation of grid voltage we can't control. That's property of the grid. And then this voltage is fixed. That's the terminal voltage. Let's say VT. That's fixed. So there are two parameters that we can control. So this synchronous generator might be connected to some prime mover. So let's say, for example, if it's a diesel engine, and then so the diesel engine, or let's say if it's a gas turbine engine, there's some form of control that you can accelerate the engine, so that, let's say for example, if it's a diesel engine, that's the fuel throttle command. So let's say some throttle command here. So if you input more fuel, the engine will accelerate. So that's one form of control that you can accelerate the synchronous generator. Since this is connected to the grid, then it's fixed at synchronous speed. So the synchronous generator speed can't change after you've synchronized it to the grid. It can only change in phase. So although you are inputting more fuel into the generator, the synchronous generator can't accelerate, so it transfers that power into the grid. So that's one parameter, and then the other parameter that you can control is the field excitation. So the synchronous generator also has a field circuit, and then it has a field voltage and field current, VF and IF, and as you remember, the back EMF or the excitation voltage is proportional to the field current. So you can control the excitation voltage of the synchronous generator. So that's B is proportional to IF, that's the field current, and the shaft speed, rotor speed. So this is pretty much fixed because you've synchronized it to the grid, so it's running at 50 Hertz, so that's fixed. So you can control the excitation voltage by changing IF. So those are the two parameters that you can change in the synchronous generator and prime mover system, the fuel input into the system and the excitation field current. So we are interested to know how, when we change these two parameters, how much power is going to be transferred to the grid. So if we have a look at the equivalent circuit, so then you'll have the excitation voltage, the synchronous reactance, and then this is the terminal voltage. That's the per phase equivalent circuit. So this is the excitation voltage. Let's say this is the terminal voltage, and this is the excitation voltage, and this is the synchronous reactance. So you can write Kirchhoff's voltage law to this loop. So you can write Vt, that's a phasor quantity, equals E plus this voltage drop across the synchronous reactance, and the current is out of the machine, so that's Is, so that's JXS I, so that's the Kirchhoff's voltage law to this equivalent circuit. So I think last week you went through drawing the phasor diagram, so you can draw Vt as phase 0, so that's our reference. The grid voltage, that's our phase 0. So you can draw a straight line for Vt, that's as at phase angle 0, some voltage magnitude, and phase 0. That's your reference. And with respect to this reference, you might have E lagging or leading. So let's say, for example, if you have a lagging current, say somewhere here, you'll have I, that's this particular current, lagging by a power factor angle of 5. So then you can draw this particular component that's perpendicular to this somewhere here. So that's JXSI. That's the voltage drop across the synchronous reactance. So the terminal voltage, this is Vt. So E is going to be this particular phasor, E. So I wrote this wrong, right? So E is going to be Vt plus JXSIA. It's not the other way. So this voltage is going to be the sum of the terminal voltage plus the voltage drop across the reactance. So E excitation voltage is the terminal voltage plus the voltage drop across the reactance. So then we draw Vt, that's our reference, 0, and then you have this particular component, that's the voltage drop across the reactance, and then the phasor sum of those two correspond to the excitation voltage. And the excitation voltage has a phase angle delta, that's what we call the torque angle. So this is the torque angle. So now from this, your the parameters that you can control are excitation voltage, that's the field current. You can change the field current and then adjust the magnitude of the excitation voltage. And then if you increase the fuel input into the system, then your power, the power you transfer will increase, and that will result in a higher current, and these angles will change as well. So we need to figure out how to relate those quantities. So we like to write everything in terms of real power and reactive power. So if we look at the reactive power, real power that's being transmitted to the grid, that's this is the per phase voltage. So we can write P equals VT IS. That's the, let's say I'll write it as IA, and then cos phi. This is the power, real power transferred per phase. So you'll have like 3 times this for the total synchronous generator. And then you have Q, that's 3 times VT IA, and sine phi, that's the reactive power that's transferred to the grid. So we are interested in writing this in terms of voltages. So E is something that we can control. So we like to write it in terms of E, the excitation voltage. So if you look at this phasor diagram, you can see that if you look at this, the arm here, that will be this particular angle, and this will be phi as well. So E sine phi, sine delta, that's the distance from here to here. So the sine of this triangle, E sine delta corresponds to this particular distance here. And then if you do XSIA cos phi, that will be the same distance as well. So you can write E sine delta is equal to XSIA cos phi. So that's from this triangle you can derive this particular equation. So then you can see that there's a IA cos phi term here. So you can write IA cos phi as E sine delta over XS. And then you can use this here for the real power equation. So then you'll have P equals 3 times VT E over X sine delta. So this is the total 3-phase power equation. So this is a very important equation. You'll use this quite a lot in power system analysis. So let's say, for example, if you were to change field current, then your excitation voltage will go up. But then your fuel input into the system is fixed. So the real power that you're transferring to the grid is fixed. So that means this particular value is fixed. So to keep it constant, the torque angle will reduce. So for the same power, if you change excitation voltage, the torque angle will adjust itself to maintain the same power input. But then depending on those values, the reactive power transfer will change. So we are also interested in writing the reactive power. So the reactive power has this IA sine phi term. So if we look at this particular distance from here to here in the triangle, you can write that as XS IA sine phi. That's this particular distance here. So that's we can write that as E cos delta minus VT. So that's E cos delta is this whole distance minus the terminal voltage gives you that particular value. And then you can write IA sine phi as E cos delta minus VT over XS. So then you can substitute this particular term in the reactive power equation, and then you'll have Q equals 3 times VT E cos delta minus VT squared 3 times this divided by xs. So these two equations are the main equations that count real power and reactive power. So as I mentioned earlier, let's say it's delivering the same amount of real power. You change E and then delta will change to maintain that same real power. But then if you change E and delta, this whole thing will change and the reactive power that you transfer to the grid will change as well. So it won't remain constant. So in the tutorials, the remaining few questions are based on these two equations. So these quantities we wrote it in terms of per phase quantities. You can also write this as line-to-line excitation voltage and line-to-line terminal voltage. Let's say if you write V line-to-line terminal voltage as root 3 VT, that's the line-to-line terminal voltage, and then E line-to-line terminal excitation voltage as root 3 E, that's the line-to-line quantities, and then you can kind of factor in the root 3's into this. You can also write it as P equals V line-to-line, E line-to-line sine delta over xs. This is the same equation, but you've written it in terms of line-to-line quantities, but there's no 3 there. So 3 is factored into these two terms. And then similarly, you can write Q as V line-to-line, E line-to-line cos delta minus V line-to-line squared over xs as well. So these two equations will be provided in the formula sheet if you have a look. So here, these two equations. So in this equation, the terminal voltage is E, notation E, and E naught is the excitation voltage. So this you have to remember the notation in the formula sheet if you're using that. So this is particularly for a cylindrical rotor machine, but then that means the reactance is constant. For a cylindrical rotor synchronous generator, the XS is fairly constant. That's a fixed value, its rotor position, it doesn't change. But then there's other types of synchronous machines called salient pole synchronous generators. For that, the XS changes with rotor position. So then that characteristic is factored into two reactances. So that's this equation. So in this course, we won't go into salient pole synchronous generators. So we'll be looking at saliency and those concepts in the variable speed drives course, mainly for permanent magnet machines and mainly for permanent magnet machines. So, but then just for your general knowledge, you remember that there's two forms of synchronous generators, and there are two equations for that. One for the cylindrical rotor one and salient pole rotor machine. So I'll do an example of the tutorial. So I'll work through the last question of the tutorial, question 8. I guess none of the tutorials covered that this week. So question 8 of tutorial says a 5.5 kilowatt 415 three-phase 50 Hertz Y-connected 4-pole cylindrical rotor synchronous motor has a synchronous reactance of 16 ohm with the field winding energized. The motor is loaded such that the armature current is 5.1 amperes at a lagging power factor of 0.8. Calculate the excitation voltage and the torque angle for this load condition. So we can draw the equivalent circuit. When you get this form of question, first draw the equivalent circuit where you have the synchronous reactance, and that's 16 ohm. So this is operating as a motor. So the current we can draw it into this system. So that will be 5.1 ampere. The motor is loaded such that the armature current is that, and so the synchronous generator terminal is at the rated voltage, so that's connected to the grid. The grid voltage is 415, so here the voltage is 415 over root 3. That's the per phase voltage, and this is our reference 0. So we need to find this excitation voltage. So now it's similar to the DC motor calculations, but now it's a phasor calculation. It's no longer a simple calculation. So here we can write this. So you have this voltage drop here. So then you can say this voltage plus the voltage drop across the synchronous reactance equals the terminal voltage. So then you'll have Vt phasor equals Eb plus JXSIA. That's the phasor equation. So Vt, so we need to find Eb. That will be Vt minus JXSIA. So Vt we know that, and the current magnitude we know that as well, and the power factor is given as 0.8. So then you can find the phase angle of the current. So Ia phasor will be 0.8, but then you have a lagging power factor that's minus, this is 5.1 magnitude, and cos inverse 0.8. Oh, do anyone if you have a pen? I've run out of the pencils, broke as well. So, all right, thanks. So here we have EB equals 415 over root 3, phase angle 0, that's Vt, minus J 16 times 5.1 phase angle cos inverse of 0.8 minus of that. So cos inverse 0.8 will be minus 36.86. So if you resolve this, you'll get the excitation voltage. So we have 201.5 and minus 18.9 volts. So this is the per phase excitation voltage. So the excitation voltage line to line will be root 3 times this. So we have 349 minus 18.9, that's the line-to-line excitation voltage. So this is the voltage, excitation voltage magnitude, and this value, that's the torque angle, delta. So part B of that question, calculate the mechanical power delivered to the load and the corresponding output torque of for this condition. So we can use this real power equation to find how much power that's being transferred through the synchronous generator. So now we know the terminal voltage, we have the excitation voltage, we've calculated delta, so there's no point in finding current. So we just substitute the values to this. So I'll use the line-to-line voltage equation. So P, that's the power, output power, is V line-to-line, E line-to-line, sine delta over XS. So that will be V line-to-line is 415, E line-to-line we found that as 349, and then sine delta. So that's, I'll write just the magnitude. We know that the power is going into the synchronous machine, it's actually, as a generator, it's consuming power, it's not delivering power, so that's why you have a minus here. Divided by XS, so that's 16. So you have 2932.16 watt power being transferred to the mechanical domain. Also, we also need to account the rotational losses. So this is the electromechanical power output, and then it says the drivetrain losses account for 120. So this is the electromechanical power, and the output power is the electromechanical power minus the rotational losses. So this is given as 120 here. So if you subtract 120, you'll get 2812.7 watt. That's the output power. So, and then you also need to find the torque. So the output torque is the power divided by speed. So when you come into synchronous machines, it's always rotating at synchronous speed. No, there's no slip involved. So the rotor speed is the same as synchronous speed. So the output torque will be the power output divided by synchronous speed. So with synchronous speed, we can find that's, let's say, 50 hertz, 4 pole. So then that will be 60 into 50 divided by a number of pole pairs, which is going to be like 1500 RPM. So this is ns times 2 pi over 60 to convert it to radians per second as well. So here, this is the output power divided by speed. That's 1500 RPM. You need to convert it to radians per second. So that's 2 pi divided by 60 here. So that's the torque. That's the mechanical torque on the shaft. And then the third part, to increase the power factor to unity, the excitation voltage is increased such that at the same mechanical loading, the torque angle reduces to minus 15.3. Calculate the required excitation voltage and the associated line current for this new operating condition. So you can change the excitation voltage and then change the power factor, but then that means the power changes as well. So let's say P equals E line to line, V line to line over XS and sine delta. So let's say under this condition you change this, and Q is given by E line to line, V line to line, XS cos delta minus V line to line squared over XS. So if you change any of these parameters, your reactive power and real power will change. But then the load is consuming the same amount of real power, so that means this is fixed. So you need to change excitation voltage and delta in such a way that you deliver the same amount of real power. But then you are achieving unity power factor. So unity power factor means the reactive power that's being consumed from the grid is 0. So this equation becomes 0. So that means we can actually cancel off V line to line. So we can write this as E line to line cos delta minus V line to line equals 0 as well. So just we remove V line to line over XS from the equation, and then cos delta will be V line to line over E line to line. So this is for unity power factor, this will be the condition. So we have the same amount of real power, so we can write sine delta as P, that's the real power, XS over E line to line, V line to line. So V line to line is constant. So now you have two equations, and then you have E line to line and delta, so you have to solve that. So for this different operating condition, V line to line is 415 volts, and P is the same as before. So that's the one we calculated here, that's 2932.16 watt. That's the real power that's being transferred. So if we substitute these values, we can, let's say this is first equation and the second equation. So we can eliminate V line to line from this. So let's say if you divide 2 by 1, you'll have tan delta, that will be P XS divided by E line to line, V line to line, and then E line to line over V line to line. So the E line to line cancels off here, and then you'll have P XS divided by V line to line squared. So that will allow you to calculate the torque angle. So then here P is this power 2932.16 times XS, that's 16 divided by 415 squared. So that will give you the torque angle. So delta turns out to be 15.3, and then you can substitute that here to find the corresponding excitation voltage. So E line to line from 1, you'll find that as V line to line divided by cos delta. So that's 415 divided by cos 15.3. which turns out to be roughly 430 volts line to line. So now you have the excitation voltage, the torque angle, and the terminal voltage as well. So you can do the calculation using the equivalent circuit to find current. So So if you draw the equivalent circuit, you'll have the terminal voltage here, that's 415 over root 3, and here, let's say 430 over root 3, and this is J16. And this angle, we found that as 15.3, but then in this case, it's delivering power, so that's a negative angle. So we need to find this particular current I, the armature current. So we have a voltage drop across here, so that will be this voltage plus the voltage drop across the reactance equals the terminal voltage. So that's E plus JXSIA equals the terminal voltage. So we want to find the armature current, so that's IA. That will be VT minus EB divided by JXS. So VT, that's our reference phase 0, so that will be 415 0 minus this excitation voltage, that's 430 over root 3 minus 15.3 divided by J times 16. Root 3 here as well. So we have 4.09 and phase angle of minus 0.0. So that's the unity power factor condition. So this is effectively close to 0. That's the unity power factor. So you should be able to draw the phasor diagram for this condition as well. So first, if you're drawing the phasor diagram for this particular arrangement, you can first draw the reference phasor. That's the terminal voltage. That's at phase 0, 415 over root 3 phase 0. That's this. So that equals EB plus this particular value here. So then you have some current. So the current here is in phase with the terminal voltage. So that's unity power factor. So that's somewhere here. That's the unity power factor current. So 4.09. And then JXIA. That's somewhere here. So we have the terminal voltage minus this turns out to be the excitation voltage, or the back EMF plus this particular component gives you the terminal voltage. So then your excitation voltage is somewhere here plus this particular, let's say, JXIS here. So this will be your E, and that will be lagging by minus 15.3. And this will be magnitude of 430 over root 3. So you have E plus JXIS IA equals the terminal voltage. That's 415 over root 3 phase reference. So that's pretty much the scope of synchronous machines for this course. So next week we'll also have tutorials on Tuesday, and the Tuesday 2 tutorials I do, I'll do it. I'll go through the other bits of the questions on the last tutorial, and then there's a final bit which is not assessed, the synchronous machines. There's a final bit which I didn't cover today. I'll do that next Friday. That's just like an overview of the like limitations of synchronous machines, and like a brief introduction to permanent magnet machines that if you are interested, you can do next semester in variable speed drives course. And then next Friday, I'll go through some of the exam material, and then like revision focused on the exam. All right.
I've got this DC motor here from a blender, and his commutation had these little black spots where if I energize the circuit,